Hello everyone. My name is Lohit Khan, and this is the last session of the introduction to interfacial labs. So today we will solve an weakly nonlinear problem in the Cartesian geometry for the where both surface tension and gravity are important. Okay. So just a moment. So let me share my tab screen first. Then I will start discussing. So today I want to show you a complete solution for the capillary for the weakly nonlinear solution for the capillary gravity case in Cartesian geometry, and we will use linked Poincare perturbation technique to solve that. It will not be possible to show you the entire steps, but I will give you the outline and the solution, and later I will show you one simulation to show the comparison with the theory. Okay, so let's start with. Remember that we will solve the standing wave solution. Okay, so your waves will not travel. So this is your domain, which is bounded. So that means the wave cannot travel, and if you have some initial perturbation, and you want to know what is the evolution of this initial perturbation at a non-linear order. Okay, so now we will solve that question. So I will directly write a non-dimensional form of the equation. Okay. So remember your length scale is sorry. This is starting from zero. This is plus L hat. This is minus L hat. Okay. So and we will non-dimensionalize based on the wave number k sum n. Okay. I will define what is kn. Your kn is the wave number that is inverse of length inverse. This is your length scale, and the time scale based on the pure gravity waves, that is square root of g kn. That is your time scale. Okay. So based on that, you will get these differential equations. That is, let's get phi equal to 0. We will assume inviscid rotational approximation. Then that is the kinematic boundary condition, the nonlinear kinematic boundary condition. And this is the Bernoulli equation at the interface. And we will assume that it is infinitely deep. So this is the condition, right? Now this term sigma is equal to inverse of the bond number. And then what is bond number? Bond number is the ratio of your gravity force by surface tension force. This is the definition. Alright. That means when your bond number is sufficiently high, then your effect of gravity is more important. And when bond number is very, very small, then your effect of your surface tension is important and we can neglect the effect of gravity. So we will use listed Poincare perturbation technique, and this is the extension in the time, that is 1 plus epsilon square omega 2. This is the extension that we will use. Okay, that means your del t will be now del tau of 1 plus epsilon square omega 2. We have already done this in the past, so I will not do this the entire step. And del t square, it will be del square del tau square 1 plus 2 epsilon square omega 2. We will not plus order epsilon to the power 4. We will not include that in our calculation. Okay. So now we can expand the velocity potential and an initial perturbation for each order like this. Epsilon to the power I phi I xzt and tau eta x tau is equal to I equal to 1 to infinity epsilon to the power I eta I x tau. Okay, so this was the solution. So for each order we will get, so for each order this all the condition boundary condition has to be satisfied, but we are more interested in these two terms. Okay, and because that will lead us to the differential equation, right? So we will get this term pi I del z minus del eta I del tau is equal to sum f I x tau, where f I is a nonlinear term. Similarly, del phi I del tau plus eta I minus sigma del square eta I del x square is equal to gi x tau. This is coming from the Bernoulli equation. This is from the kinematic boundary condition. Okay. Now I can expand phi I and eta I. So I need to find a solution for phi I and eta I, so that the governing equations can be satisfied, the boundary conditions can be satisfied. Okay, so there is another boundary condition. It will be del phi del x at x equal to plus minus of k in hat is equal to 0. This is one more condition. This is no penetration condition. So I need to find a solution for phi I and eta I, so that differential, so that the boundary equations and the boundary solutions and the boundary equations and the governing equation are satisfied. Okay, and we will left with some. Then we will substitute everything here, and we will get an ordinary differential equation. We have to solve it. Okay, to find a temporal dependence. So now it will be j equal to 0 infinity aij term cos alpha j m x to the power alpha j m z x tau equal to, what is alpha j m? It is coming based from the initial condition. I will tell you what is the initial condition. The dimensional initial condition is eta hat x hat 0 is equal to cos km x hat. This is a dimensional initial condition. Okay, and this form is related to that fact. Here alpha jm is equal to kj hat divided by, sorry, kj, k is a dimensional quantity, kj by km. This is your alpha jm, right? Okay. So now I will substitute our expression to this two equation, and we will finally get this two equation. One equation is 0 to infinity alpha j m aij minus ai. Remember that aij is a function of tau. Okay, minus dcij d tau cos alpha j m x is equal to a phi x tau, and another will be j to 0 daij. So this was the equation. And the initial condition is theta x0 is equal to, this is a non-dimensional form, right? Epsilon cos x, and eta dot x0, that means the initial velocity has to be equal to 0. Okay. Now for the linear order, the right hand side is 0. That means at order epsilon, your f1 x tau is equal to g1 x tau equal to 0. Okay. So we will get at the linear order that alpha jm from these two equation, we will get alpha jm a1j minus dc1j d tau equal to 0, and dA1j d tau plus c1j into 1 plus sigma alpha jm square is equal to 0. Okay. Now it has to be started with this initial condition that c1m 0 is equal to 1, because only at the mth mode there is a value, other values are 0. Similarly, dc1m d tau at tau equal to 0 is equal to 0, because the initial velocity has to be 0. Now using these two conditions and putting it here, we will get a1m 0 is equal to 0, and dA1m d tau at tau equal to 0 is equal to minus 1 plus sigma. Okay. Now for any other values of j which is not m, we will have c1j 0 is equal to 0, dc1j d tau at tau equal to 0 is equal to 0, and a1j 0 is equal to 0, and dA1j d tau at tau equal to 0 is also equal to 0. All right. Okay. Now for j equal to m, we have, let me write down the equivalent equation, dA1m minus dC1m tau equal to 0, dA1m b tau plus C1m into 1 plus sigma equal to 0. because remember alpha mm is equal to kj by km is equal to 1. Okay, so alpha jm square is equal to 1 here. So we can combine these two very easily and we will get d square a1m d tau square plus 1 plus sigma a1 m is equal to 0. So here let us define omega 0 m square equal to 1 plus sigma. So now this is the non-dimensional frequency of the capillary gravity waves. So can you realize what is this term? So let me just write that down. Sigma is equal to 1 by bond number and your bond number is equal to rho g by t sum km square. True. So sigma equal to t km square by rho g, and this is the non-dimensional frequency. Now what will be the length scale? Or sorry, what will be the scale for the dimensional frequency? That's some WC square. WC square is nothing but G into Km. WC square is equal to G into Km. So WOM square, WOM square, how can I write it? It is WOM hat square dimensional divided by W omega C square. Okay, that is the scale of the frequency is equal to 1 plus Tkm square by rho G. Now, so what is the dimension of the frequency is equal to Wc hat square into 1 plus Tkm square by rho G. And what is omega C square? Omega C square is G into Km, 1 plus Tkm square by rho G. So is equal to Gkm plus Tkm cube by rho. So 1 plus sigma is sigma is the non-dimensional form of this term. We are very familiar with this term. Okay, so this is 1 plus sigma. All right. Now, so what will be the solution of that equation? One solution to the equation a1m is equal to some a1 cos omega 0 m tau, where omega 0 m square equal to 1 plus sigma plus a2 sine omega 0 m tau. Now, a1m 0 is equal to 0 implies a1 equal to 0 and dA1m d tau at tau equal to 0 is also equal to minus 1 plus sigma, right, is equal to a2 omega 0 m. Now minus 1 plus sigma is equal to omega 0 m square. So what is a2? A2 is equal to minus of omega 0 m. Okay. So your a1m tau is equal to minus omega 0 m sine omega 0 m tau. All right. And if I substitute this in this equation, dA1 d tau, then I will directly get an expression for C1n. So let us do that. So I will get minus omega 0 m square cos omega 0 m tau plus C1m omega 0 m square is equal to sigma. No, so sorry. Yes, it is 0. Okay. So this is omega 0 m square, this is omega 0 m square. So your C1m is equal to cos omega 0 m tau. Okay, so your phi 1 in z tau is equal to minus omega 0 m cos x sine omega 0 m tau e to the power of z, because alpha m is equal to 1 and eta 1 x tau is equal to cos omega 0 m tau into cos x. Okay. Now, so for the linear order, your f1 and g1 are 0, but it will not be the case for the non-linear order. Okay. Now we will calculate f2 and g2 for order f7 square. So order f7 square. So now f2. So this is the full differential equation at z equal to eta. Now we are applying it at z equal to 0. So we will get contribution from this term, okay, because it will be del square phi del z square into eta 1 eta. That will be one contribution, and this term we will get contribution at second order from this term as well. It will be del phi 1 and del x into del eta 1 del x, right? And now we are pushing this of the nonlinear term, so the sign will change accordingly. Okay, so this is the whole idea. So f2 will be del phi 1 del x del eta 1 del x minus del square phi 1 del z square eta 1. Similarly, g, okay, so let me just write down the final expression for f2. This is so we already know the expression for phi 1 eta 1, right? So we can do the calculation, and for Cartesian geometry the calculation is easy. I am writing down the final expression. You will get omega 0 m cos 2x into sine 2 omega 0 m tau. Okay, so this is the expression, and for g2, expression for g2 will be like this: half del phi 1 del x square plus del phi 1 del z square z z eta 1. Okay, so now if we do the substitution, we will get an expression for g2 as well, similar expression, right? So this is the term. Now, so now we will do again the similar calculation for different j's. So remember, for each I there are infinite number of j can be present. Okay, so this is written in our summation. See, for each order of I there can be, there is the summation is over j, so there can be infinite amount of, so j indicates the modes. Okay, so the many modes can be generated. Okay, we will do that. So now for j equal to 0th mode, equal to 0. So first let us write. Okay, so let me write down the expression for G2 as well. Plus 2x into cos 2 omega 0 m tau plus 2 cos omega 2 omega. Okay, so this is the expression for G2 for j equal to 0th mode, because the summation is starting from j equal to 0. Okay. see that here for j equal to 0 for second order, your c20 is equal to 0 and dc20 d tau at tau equal to 0 is equal to 0. Okay. Now equation for the second order, it will be like this: d tau plus c20. Now alpha 0m is equal to 0. Okay, you need to keep in mind. Half into 1 plus sigma cos 2 omega 0 tau and and also the differential equation will be just just check the equation for any j, and you will find that for g equal to 0, the differential or the second order differential equation will be reduced to this term. Okay, so your a20 tau will be, so I'm writing down the final expression for a20 tau. Your final expression will be, let me write. That will be some constant c1 plus omega 0m by 4 into sine 2 omega 0m tau. Okay. Now you see that from the it is cos 2x plus a constant into cos 0x into time dependent term. So it is only cos 2x plus cos 0x. So there is no contribution of cos x or cos 3x or 4 cos 4x, right? So j equal to 0, that means j equal to 0 integrate cos 0x and j equal to 2m. J equal to 2m means cos alpha j m x is equal to cos alpha 2m comma m x, and alpha 2m comma m means 2m means cos k 2m by km x is equal to cos 2x. Now here I am saying that k2m will be 2 into km. Why is that? Just think it yourself. Okay, you need to figure that out. Why? Why k2m is equal to 2 into km? Okay, just figure that out. I will give you a hint from the no penetration boundary condition. You will get that answer. Okay, so only at j equal to 2m we will get. So we need to solve the differential equation for j equal to 2m. Okay, and let me write down the expression: 2 into a2 2m minus bc2 2m d tau is equal to half omega 0 m into sine 2 omega 0 m tau, and dA2 2m d tau plus c2 2m 1 plus 4 sigma, that is alpha 2m m whole square, that is 4, because alpha 2m comma m is equal to 2 is equal to 1 by 4 1 plus sigma into 1 plus cos 2 omega 0 m tau. So I will convert it to a single differential equation first, but first let me write down the uh, constant, the initial the constant term, that is this is at t equal to 0, c2 2m is 0. Similarly, dc2 2m at tau equal to 0 is 0. As this is 0, so as a consequence, a2 of 2m will has to be 0, because this also indicates a velocity term, but this term is non-zero. and you will receive this term from this expression. Okay, just figure that out. You will finally receive this term. So now you can solve the expression for a2 of 2m. Okay, and see that for any other term you will not be getting any solution for solution for j equal to m or 3m or 4m or 5m. Okay, you will not be getting any solution. If you want to calculate, you can do that, but finally you will be able to get that the result is 0. Okay, because this is in the cos square of x that we get in the second order. It has projection for j equal to 0 and j equal to 2m only. Okay, so finally you will get your answer accordingly. So after solving a2 to m, the differential equation, you will just combine this and you will find the differential equation of it for a2 to m. Then you can get the expression for a2 to m, and similarly you can get the expression for c2 of 2m. Okay, and you plug those in the expression for phi 2 and eta 2, and then you will be able to find out the answer. Okay, so we are interested in the evolution, so your final answer also looks like this. Your final answer will be eta 2 equal to, there will be some constant term plus come again some constant term into cos of 2 omega 0 m tau plus some constant term into some new frequency term, that is cos omega 2 m tau. Okay, multiplied with cos 2x. Okay, now there will be no contribution from cos 0x for eta 2. Why? Because it needs to satisfy the eta xt dx minus KLL hat KLL hat equal to 0, this condition for each order. If I have any contribution from the zeroth order, then this term will not be equal to 0. So it will then defy the physics of the problem, because this is incompressible flow and the volume cannot increase. So there will be no contribution from the cos 0x term for, for the expression for eta 2. Only for eta 3 you can proceed like this, and for eta 3 we will get contribution at j equal to m and j equal to 3m. Okay, now remember that the contribution at j equal to m, that will be a secular term. We have solved many problems using the least state Poincare perturbation technique, where with at some order we need to eliminate the frequency correction term. The frequency correction term appears here also. At the third order, you can eliminate the frequency correction term. So at the third order, at order epsilon q, you will get the value of the frequency correction term omega 2. Okay, you will get some expression for that. Now plugging on this omega 2, then you can go again further and solve for the higher order also the problem. Okay, but we will stop the problem at the second order. So we will solve the so we will so your eta x tau eta xt now, because after getting omega 2, then you multiply, then you just make this transformation tau into 1 plus epsilon square omega 2, then you will find the expression of what will be the t, because all the problems we have solved in terms of tau 1. If you multiply with 1 plus epsilon square omega 2, then you will get back the expression t, and your eta xt will be epsilon eta 1 xt plus epsilon square eta 2 xt. This is your expression. Okay. Now I will show you a result for this particular problem. Okay, I will show you a comparison with the simulation as well. Okay, just give me 2 minutes and I'll be back. So pardon the interruption. Now I will show you one a comparison of this solution. Okay, so let me share my screen. Yeah. Yeah. So you see here I have plotted my analytical solution. So the analytical solution are the solids line in this plot, okay, and the simulations are the dotted line. So here the simulation domain is 2 centimeter. Simulation domain is 4 centimeter. It starts from 0. So plus L hat is 2 centimeter, minus L hat is minus 2 centimeter. So here I have started with this initial condition A0 of cos qx, kqx, okay, but kq is equal to 2 pi. And your epsilon is your non-dimensional initial amplitude, that is the value of 0.5. Now your linear theory only work when epsilon is 0.01 or zero point 0.1 for very small value, but for higher value, your theory, your linear theory doesn't agree with the solution. Okay, so here in this plot, you can see that the the solid line is agreeing quite well with the dotted line. Okay, you can see that from this red solid line and green dots, you can see that they are almost overlaying on top of each other. Similarly, this blue, I don't see the if you, I don't know if you can see the blue lines, but there is a blue line on the and and on top of that there is a dark green dots. They are agreeing with each other, and for the sky blue solid line, that is from theory, and it is agreeing quite well with the green dots. Okay, so you can see that your theoretical result is agreeing quite well with the simulation. So that is the outcome of this solution. Okay, all right. So so uh, so as today is the last class, so let me go over a quick recap of whatever we have done in this course. All right. So let me share my screen again. Okay. So we have done some problems in the class in the Newtonian mechanics framework. where we have solved some linear problem. Okay, we have solved the problems for this kind of system. Okay, we know how to we know how to solve this problem. Here we have implemented our normal mode analysis. We have discussed about those problems where if forcing where we have applied forcing to this kind of system. Okay, and we have solved this with those kind of equations. We have included damping in our system and we have solved those. We have also solved the complete for the pendulum equation for the governing equation of this kind, x double dot plus sin x is equal to 0. We have solved this using the complete and using the Jacobi elliptic method. Jacobi elliptic function, as well as we have solved that using perturbation technique. We have solved the problem where for the problem for the Kapitsa pendulum. Right, and there we have implemented Floquet analysis. What is Floquet analysis? Floquet analysis is the generalization of normal mode analysis. Floquet analysis is the generalization of the normal mode analysis, and we have done that. Now after that, we have moved for solving the fluid mechanical problem. We have solved problem for the pure gravity waves. They are for infinite depth and finite depth as well. For the infinite depth problem, your dispersion relation is omega squared is equal to gk, and for finite depth is gk tan h kh. Now, when this problem can convert it into this problem when your kh is much greater than 1. That means your h 2 pi by lambda into h is much greater than 1, or h is much greater than lambda. For this case, we can solve the problem. Okay, when h is your very greater than lambda. Okay, now for shallow, it converts to tan h kh is nothing but simply kh, and it will be g k square h, and this is this is non-dispersive wave. What are the non-dispersive waves? Non-dispersive waves are those waves whose phase field is independent of the wave vector. Okay, that means c is equal to omega by k is not a function of k. These waves are called non-dispersive waves. So the gravity waves in the shallow water is non-dispersive waves. Now we have solved capillary gravity waves as well. For the capillary gravity waves, what is the And what is the relation for the deep water dispersion relation? Gk plus Tk cube by rho. Okay, this is the dispersion relation. We have plotted we have set the criteria. We have defined a length scale L. L is 2.7 millimeter. That is, this is the capillary gravity length scale for the air water interference. Now when your x is greater than L, then it is gravity dominated. Much greater than L. And when x is much less than L, it is surface tension dominated. I have shown you the graph that c square with respect to k, right? C is nothing but omega by k. So this is the gravity dominated region, and this is the surface tension dominated region. Okay. Now, why do we get this kind of curve? See that omega square is equal to gk, and c square is equal to g by k for pure gravity waves. That means the curve is hyperbolic, and for pure capillary case is omega square equal to tk cube by rho. So c square is equal to omega square by k square is equal to tk by rho. So it is a straight line with respect to k. So this is the part. Okay, and this is the region where both gravity and surface tension both are important in the to determine the dynamics of the problem. Okay, so we have decided all this equation. Now, we have also talked about Rayleigh-Taylor instability. Where we have considered two different fluid systems. This is fluid system 1, this is fluid system 2. If rho 1 is greater than rho 2, then this is a stable system. Under which condition? Under surface tension or gravity. Okay. Now, if rho 2 is greater than rho 1, then this is unstable system when your size of the container is large. That means in the gravity dominated region. But for very thin, container, suppose like this, then even if rho 2 is greater than rho 1, the system can be stable. Why? Because in that case, your surface tension acts as a stabilizing agent. Okay, your surface tension acts as a stabilizing agent, and it can stabilize the system when the domain size of your geometry is very small. Okay. Then we have talked about Rayleigh-Plateau problem. What is Rayleigh-Plateau problem? Rayleigh-Plateau instability. Rayleigh-Plateau instability is the instability of jet. Okay, instability of the liquid jet of like this. If you provide The question is, if you provide some perturbation in the form of eta equal to r naught plus a naught cos kz. This height is r naught. This is the undisturbed liquid jet radius, and this is your r direction. This is your z direction. The oscillation is along the z axis. Okay, r naught plus a naught cos kz. Then you ask the question: Is this situation stable? Then, under certain criteria, when k r naught is less than 1, then you situ then this then your we get it from the dispersion relation. Just check the dispersion relation. I do not remember the exact formula for that, but we have derived the case that when your k r naught is less than 1, then your system is unstable. Okay, in axisymmetric. For full 3D case, always stable. stable. Now, when your system is unstable, your linear theory predicts that your linear theory predicts exponential growth, but that doesn't happen actually. What happens in reality that it breaks, and it creates small droplets. Okay, so the shape is initially like this, then the it will form something shaped like this, and it will break from here. Okay, so and it will create some droplets, and droplets like this. Okay, so you can see this phenomena on the spider web. Okay, so on the spider web, you might have seen small droplets. So these droplets that appear because of the relative instability. Okay, suppose there is a how can you treat this problem? You can treat this problem like this. There, the spider web is some solid material. The water, this is the water, and any perturbation, that perturbation is coming from the nature. It creates some waves like this, and the droplet breaks because of the relative instability. Now we have discussed about this. We have also discussed about hollow cylinder, where outside is fluid and inside material is water. And what is the stability criteria for that? We have discussed that in our during the course. Okay. We have also discussed the course where where there is some inner material. This is the situation for the spider web. Okay. There are some there is the inner core, and we have discussed what will be the stability criteria for this kind of problem. We have derived the entire equation for that. Okay. Then we have discussed about the shape oscillation of sphere. We have a sphere like this, and we provide some kind of perturbation. Okay, we provide some kind of perturbation. Hmm, what I can do, I can show you some solution, okay, that we can provide that we can provide to the this kind of problem. Okay, so let me share. Let me give me a moment. I will be able to share my screen. So let me now share my screen. Okay, I will show you some perturbation on sphere. Okay, so I will tell you what I am doing. So see here, this yellow, this yellow thing is an original sphere. Okay, this yellow, this is the original sphere, and blue one is the perturbation on the sphere, and this is P2. This is legendary P2. I am plotting it in Mathematica. So I will show you some perturbation on it. Okay, so see that here it is a little bit. Uh, so it is a so you can see that this is almost symmetric. Okay, let me just reduce the figure size a little. Yeah, now it is fine. So see, you can see that it is little bit squeezed at the north pole and south pole, but on the east and west, it is slightly spreaded out. Okay, so it is almost a symmetry, right? Now, if I increase the size of the initial perturbation, it will be something like this. Okay, now you can see that it is a distorted shape, but it is an allowed shape. Okay. Now, when your initial amplitude is 0.5, that you can see that the shape that is a shape of a nut almost. It is shape of a whole peanuts. So now you can see that the shape is very different from the sphere, and you can expect that linear theory cannot agree here. But for this perturbation, it is almost a sphere with a little bit distortion, so linear theory can work here. Okay, but I will show you for the larger amplitude where you can clearly see the difference, and you can see the how the shapes are looking. Now for legend P3, yeah, for P3 you can clearly see three lobes. Okay, that's why the name comes the P3. Now for P4, we expect that four lobes will appear. You can see there are four lobes, but see the beauty that these are all symmetric. All of them are symmetric. So maybe for P5, P5 is some kind of shape, and you can see almost five lobes. Six, there are six lobes like this. Now we have discussed that all of this perturbation is volume preserving at a linear order. Okay, all of this perturbation are volume preserving, so all of them are allowed perturbation. But we have talked, but P1 is a special case, right? We have discussed that for P1 there is a shift. There is a small shift in the say. There will be shift in the center of mass. Okay, so let us try for legendary P1. Yeah, maybe make the initial perturbation a little small. Then we can see. Right. So you can see that for small perturbation, it is looking like a sphere, but it is not symmetric. See that it has moved slightly right on the right hand side. Okay, it has slightly moved on the right hand side. That this indicates that it retains its shape at the linear order, but its center of mass, the position of the center of mass has changed. Okay, so this is the whole idea regarding the P1. But we have discussed that for P1, the center of mass, position of the center of mass will change. As a result, its omega square will be zero, and we are seeing it. We are seeing it here. Okay. Now, what will be P0? I don't know. Yeah, and we have discussed that for P0, P0 is not an allowed mode, because for P0 its volume will change. We have discussed that. If we P0, so that's why P0 is not an allowed mode, but an incompressible flow. So we are seeing it here. The yellow one, is the original sphere, but the blue one is the P0 mode. After applying the P0 mode, and we are seeing there is a volume has its size has become bigger. That means its volume has been changed. Now, if I put one minus, then this volume will shrink and you can see them. Okay, so these are some perturbation that we are going to use, that we have used on the sphere. Okay, and we can solve it entirely the problem from the linear theory when your initial perturbation is small. Okay, all right. Okay. So we have talked about the shape oscillation of sphere, that P1, P2, etc. etc. all are allowed mode, but P0 is not allowed mode because it does not preserve volume, and omega squared is equal to 0 for P0 and P1 as well. For P0 is just it is just increase or decrease in size without any oscillation, and for P1 it is just translation without any oscillation. Okay, but for P2, P3 dot etc. you will get an omega square. Alright. Now we have also solved problem. We have solved the Cauchy-Poisson problem. There I have provided you some initial conditions. Therefore any arbitrary initial perturbation, you are asked to solve the problem, and at the linear order you can solve that problem exactly. Okay, that is the Cauchy-Poisson problem. We have solved the Cauchy-Poisson problem in Cartesian geometry, in cylindrical geometry, as well as in spherical geometry. Here it will be some summation of cos knx. You can express your initial perturbation as some summation of cosine knx. For the cylindrical geometry, you can express it as some cosine j0 knr, and here you can express it as some pn of x. Okay, in the spherical geometry, and we have solved it for all cases, and the solutions are provided. You can use that solution to find the solution, find the result. All right. Now, apart from this, we have also solved problem for the Faraday instability. There we have talked about the case where we are provided forcing on the bottom of the interface. Okay, that's which makes your pressure, your initial pressure, a time dependent variable. Okay, your base state pressure, and we have solved the problem, and we have derived Matthew equation from here, and we have solved the problem using the multiple scale method. Okay, and I have shown you the stability diagram for this kind of chart. We get this kind of shape, this kind of shape. Okay, we have talked about that. Now there is one thing that I haven't discussed, but it is discussed in the class. That is the Kelvin-Helmholtz instability. There, there you have to talk about two fluids, and there are some distribution in velocity. Okay, in both fluids, and you need to figure out this the stability criteria of the interface. Okay, you will eventually get a dispersion relation over that, and there are some questions in the assignment which will be very easy to understand from the dispersion relation. So I will not go over it. That one interesting thing that you will see, that in the sometimes in the cloud you will see some interesting pattern like this. You will see clouds are shaping like this. This appears because of the Kelvin-Helmholtz instability. These are called biloclouds. Okay, so That's all about the Kelvin-Helmholtz instability. There are some questions in the assignment and the solutions are also provided, so it will be easy. It will be easy for you to understand. All the questions can be solved using this from this dispersion relation. Okay, and we have also talked about the non-linear waves. We have talked about non-linear waves in the cylindrical geometry and in Cartesian geometry. And I have shown you the result that so your linear theory only works. Linear theory works when epsilon your in that is your nonlinear initial amplitude is much smaller than one. Okay, linear theory works fine there, but linear theory fails when epsilon is approximately equal to one. If epsilon is of order 1, that means 0. 0.3, 0.4, 0.5. For these cases, linear theory fails to achieve the accuracy. In the weakly nonlinear regime, overshoot occurs. I have discussed about overshoot. That means the height of the interface is so. If I draw a picture, it will be better. So initially, suppose your wave is starting from here. This blue one is the red one is the initial interface, and green one is after one time period. If the green one is something like this after one time period, that means you can see that this height is large. This height, so there is an excess height. It's this high, so the interface moves beyond its initial perturbation after one time period, so it indicates an overshoot is the excess height. Okay, so this overshoot is the property of the nonlinear theory. This is not the property of linear theory. In linear theory you can never see the overshoot. Also, I have discussed about the linear theory. The nodal point, the position of the nodal point is always fixed. But in nonlinear theory, you will see moving nodal points. Okay, and that can be captured by the weakly nonlinear theory. Okay, there is also one thing called the dimple formation that can be captured in the weakly nonlinear theory. Dimple formation is something like this, that it occurs for the pure capillary. For the capillary, when the surface tension is involved, that that you have some initial perturbation like this, it comes down, and when it rises, it forms a small shape like this. Okay, it's small shape like this. You can see that for the linear theory will predict something like this. The linear theory will predict something shaped like this. This small change, this small curvature change, the shape this coming down, and suddenly this shape. It is called dimple. It is a property of the nonlinear theory. And from the nonlinear theory, we can capture that. Okay, so we have discussed about all these things. Okay, and I have shown you the solutions. I have shown you the comparison with the simulation as well. That agrees well when your epsilon is of order 1. Okay. Okay. So that's all that we have done during the course. If you have any further query, you can ask in the forum. And if you are appearing for the exam, then I wish you best of luck. Okay, and I will post this video lecture record of this video lecture on my in my YouTube channel. You can see it there, and I will post all the documents in my G drive, and you can collect it from there. Okay, and I wish you all the best and goodbye. Okay, that's all for today.